Afternoon bag hosted by the Department of Geography and Geology. This afternoon's presentation is by Matthew Rahamut, a postgraduate in geology, and he is, as you can imagine, a graduate of our department, where he graduated in 2016 with first-class honors. No easy feat, and so we should recognize that. He then went after graduation to work at the Institute of Marine Affairs in Trinidad and Tobago before returning to Jamaica to begin his postgraduate studies. He's currently in the third year of his MPhil in geology, and his research interests include neogene coral reef dynamics in the Caribbean, carbonate sedimentology, and coastal geomorphology. Today's talk is entitled The Late Pleistocene Coral Reefs of Treasure Beach and Rio Bueno, Jamaica. So he's looking at the south coast with with Treasure Beach, and the north coast with Rio Bueno. So the late Pleistocene coral reefs of Treasure Beach and Rio Bueno, Jamaica, biofacies, taphonomy, and accretion. And so the talk will examine the deposition of ancient coral reefs during the last interglacial warm period, approximately 125,000 years ago, a time when sea levels may have been up to 6 meters higher than the present. In his talk, he's going to examine how these reefs responded differentially to global sea level changes, as well as local environmental stresses. I'm sure, like all of you, we look forward to hear Matthew's presentation. Matthew, over to you.
Okay, thanks. Let me just share my screen. All right. Can you hear me?
Loud and clear, Matthew.
All right. So, thank you for the introduction, Dr. Edwards. So I'll just get right into it. So we were talking about the last interglacial warm period. So in particular, when we talk about the last interglacial warm period, we're looking at 128 to 116,000 years before present. At that time, temperatures would have been about 1 degree higher than pre-industrial times. Carbon dioxide was still less than 300 parts per million. It's now 400, it's now more than 400 parts per million. And there would have been an ice volume, the Greenland ice volume would have been about 25% less than today. And that led to sea level being about 6 to 9 meters higher than present. So that's the context that we're using to examine these coral reefs. So how exactly sea level changed during the last interglacial period is some subject of debate. So people have many different models for how it changed. They fall into more or less 3 categories. So there's one sea level peak, which you can see in the Western Australia one. There's one sea level peak that forms the marine isotope stage 5e. There's intervening low stand, which is another model, and that one usually comes from Barbados. So they use an erosion surface that they infer to be intervening low stand during the last interglacial sea level. And then there's also another one, which has sea level rising, having a period of stability, and then another rapid period of rising. And that one usually comes from, that one is from Yucatan, and it's usually associated with reef drowning. And you can see it there with Blanchon et al. 2009. So by the end of the talk, I'd like to see if any of these, which one of these, or do we see evidence for any of these fitting the reef deposition in Jamaica, in those 2 areas. Now, in the context of sea level rise, tectonics is also a very important factor. So in areas where we have very rapid uplift, in areas where we have very rapid uplift, we can see different cycles of sea level rise exposed subaerially in fossil reefs. In areas where there's rapid subsidence, sometimes all of the cycles of sea level rise. So for example, in subduction zones, all of the cycles of sea level rise and fall are below water. So that's the global context to sea level rise and how it affects reef architecture on a large scale. On a smaller scale, we can use taphonomy to actually look at some of the processes that take place on a reef. So the basic, well, taphonomy is all the postmortem processes that organic remains undergo. And it's very useful to tell us how the organism died, what happened to it after it died, and how long was it exposed to taphonomic processes. So how fast was it actually buried? And that's the whole concept of the taphonomically active zone, which we might talk about a little bit later. And that's very important in refining some of our paleo-environmental reconstructions. And this is an example of some of the taphonomy of a coral, where we have our passive borers, like we see in the first one on the left. And then following that, we have our active borers, overgrowth, sediment occlusion, finally burial, and then it's out of the taphonomically active zone. And using taphonomy, it allows us to do a few things. One of the useful things it allows us to do is if we have coral species, Acropora palmata is a good example, that can occur in different environments. We can't use the coral species on its own as a paleo-environmental indicator. So Acropora palmata can occur on keys, it can occur in subtidal regions, it can occur in intertidal zones, and different taphonomic markers can help us determine where exactly it's from. And when we're doing coring, especially on Holocene reefs, taphonomy becomes very important. And in addition to that, using taphonomy, combining it with our knowledge of biophases, it allows us to look at how coral reefs respond to sea level rise. So coral reefs can have three main responses to sea level rise. One is to keep up with the sea level rise, which you can see here in the little graph. So one is to keep up with sea level rise. Before they can keep up with sea level rise, they have to catch up with it, which you can see in number 2. And then finally, when sea level rise outpaces the reef growth, they give up. So we have 3 phases: the keep up, the catch up, and the give up. And we'll see if any of those can apply to some of the reefs that we look at. Now, the way that we can interpret the fossil record is based on our understanding of modern reefs. So corals tend to carve out their own space along the reef track, depending on how much energy they devote to reproduction or self-maintenance or growth. And based on that, they tend to carve out their own little zone along the reef track. And if we know that, then we can infer the paleo-environmental zones in fossil reefs. And this is based on the Gora and Gora 1973 model, which is based right here in Discovery Bay, Jamaica. And so far it's been found to be useful in interpreting the fossil record. And if we have an idea of the paleo depth of these species, it's also useful in determining uplift and subsidence rates. So if we know the elevation, we know the paleo depth, and we know the age of the species, then based on that, we can determine if we have subsidence taking place, what's the rate of subsidence, or if we have uplift taking place. And that's been done recently in Jamaica, as you can see on the graph on the right-hand side. The 2 areas that we're going to be looking at, the Treasure Beach and Rio Bueno area, you can see them here. So Rio Bueno is more or less where it should be, considering sea level at 125,000 years ago. Great Bay and Paul's Point, which is close to Frenchman's Bay in the Treasure Beach area, those have experienced subsidence. So the geologic context of all of this, we're looking at the Falmouth Formation. And that's the last interglacial warming. That's the reefs that were deposited during the last interglacial warm period. It's the youngest member of the coastal group, which would have been deposited when we had our mid-Miocene uplift that would have caused the depot center to move seawards. So it's a mix of tectonics with sea level changes superimposed on it. And the youngest member of that is our Falmouth Formation. In southwestern Jamaica, there's also the Port Morant Formation, which is a mixed coral clastic system. It's also the same age as the Falmouth Formation, and we find that in St. Thomas. So the research questions that I'd like to look at are, what are the possible changes how are possible changes during the last interglacial warming period reflected in the emergent reef species at Treasure Beach or Rio Bueno? And what may account for the differences in facies patterns between these two localities? And in order to do that, we're going to characterize and quantify the taphonomic signatures in the late Pleistocene corals. We need to ascertain the extent to which, or if at all, sea level changes during the last interglacial can be detected in the late Pleistocene coral reef deposits. And then we can use that to reconstruct an accretionary history of the late Pleistocene coral reefs using the taphonomic signatures and the facies characterization. And these are the proposed areas, well, these are the areas that we're studying. We're looking at Rio Bueno on the north coast, and then Treasure Beach on the south coast. And these were selected because they have probably definitely the best exposures of the Falmouth Formation, so the best preservation of the Falmouth Formation. Treasure Beach in particular has a huge diversity of facies, and also because of, as stated before, some of the possible tectonic differences and paleo-environmental differences between the north and the south coast. So the first thing I did was fieldwork to document the outcrops and identify the reef and other sedimentary fishes. After that, I collected coral samples from the lower, mid, and top of each of the units where they're accessible. And in Treasure Beach, I focus mostly on the top unit because that's the one that's accessible. In Rio Bueno, I collect throughout the entire section because Rio Bueno is also very accessible. So after collecting them, I sort them into slabs. So 4 slabs per specimen, and I try to get the slab thickness to be as even as possible. Now, following sorting them, I photograph them and then I run them through ImageJ. ImageJ is useful to an extent in working out the secondary porosity of these corals. It can be tricky when you have sediment occlusion because then you have to characterize it individually. But for the most part, it's useful in working out the secondary porosity of the corals. I set the scale, and then after I work out the secondary porosity, I can go in and individually characterize whether it's due to macro boring or dissolution or just unidentifiable features. So these are the localities that we're looking at. These are the localities that we're looking at. So this is Treasure Beach on the left-hand side and Rio Bueno on the right-hand side. You can see the localities that I visited in Treasure Beach. So all the way from Billy's Bay down to Great Bay. And at Rio Bueno, that's a continuous stretch of late Pleistocene coral reef. In Rio Bueno, it's a bit different. There are 2 very good exposures on the western and the eastern end of Rio Bueno. So on the eastern end, I think, well, one of the exposures is probably covered up by vegetation by now, but Scenic View has a very good exposure. And then on the western end of Rio Bueno, there's a very good, classified, but still very good exposure of Acropora palmata, which we'll get to in a bit. So these are some of the observations at Treasure Beach. The first observation is that we have these planed off surfaces of hemispherical corals that you can see in E. So this is a planed off surface of Pseudodiploria strigosa, and it's at the base of the Acropora palmata stance. At B, you can see you have these large in situ Acropora palmata stands. They're about 1.1 meters high, and they're monospecific. So it's just Acropora palmata in there, and that might be useful in helping to describe our deposition model. Following that, if you look at D, you can see that there's some siliciclastic beach rock. Doesn't form too much of the scope of my research, but it's still useful to know. So it's siliciclastic, and it contains some marine fossils in it. So it could have been maybe a sand wave that was migrating across the reef after it had already died. So that is Great Bay. In Tranquility Bay, it gets a little more interesting. So what you can see in D is that you have this in situ with some ex situ Acropora palmata, and overlying that, we have these large patch reef structures, and you can see a close-up of one in A. That's on the eastern side of Tranquility Bay. On the western side of Tranquility Bay, we still have the same Acropora palmata, class stands, but instead, what we have on top of that is this very thin layer of lagoonal facies. So Parietes fracata, and these are fragmented corals, and they're all encrusted by Siderastria radians. Now, this layer itself is no thicker than about 20 centimeters. And you can see the difference in C, you can actually see the difference in the height. And that's all due to just differences in reef geomorphology. At Frenchman's Bay, at A, there's a possible paleo notch. Not too sure about it, but it's still a useful feature. The most useful feature that I saw there was B. Now, these are hemispherical coral heads, and they're all about 40 centimeters high. They don't get above that, and most of them don't get below that. So they're right at 40 centimeters high. And we can use that again to infer something about the depositional environment. Some of them have been planed away, so the tops of them have been eroded, and then it's been recolonized by Siderastria radians, which you can see in C, right? And then finally, west is Billy's Bay. So we have this thicket of Acropora cervicornis. We have calcareous algal tubes, and we have some Acropora rubble. This is over an irregular surface where we have some massive coral heads, and these contain, and that's overlain by coral rudstone. So this is the paleo geographic reconstruction. It's the only one that I could find of Great Bay, and this is by Henry and Head, 1984. It's the only published one I could find. And it focuses a bit more on the study of the beach rock, but this is still the published paleo geographic reconstruction. And this is mine. So I focus more on the reef facies. I've set the sea level to be about 6 meters higher. So that's where it would have been if the assumption is correct, at 125,000 years ago. And I've divided up into 5 facies. So we have this heavily encrusted in situ Acropora palmata stance in Great Bay. We have the patch reef structures composed of Corpophalia natans, Pseudodiploria strigosa, and Pseudodiploria clivosa at B1 here at Tranquility Bay. And then we have back reef to lagoonal facies consisting of Parietes fracata, some common Parietes asteroides, and I found a few fossils of Isophyllastria rigida. All of these are associated with back reef, lagoonal deposits. So you tend to find these a lot in seagrass environments. And then C, we have the eroded Parietes strigosa coral heads encrusted by Siderastria radians. And then finally at D, we have the rudstone consisting of ex situ Acropora palmata, Acropora cervicornis, surrounded by carbonate bioplastic sand. And this is the distribution of the fishes. So this is running from Billy's Bay to Great Bay. And what I've done from Frenchman's Bay to Tranquility Bay, you kind of have to, you can see there's some difference in the upper and the lower layers, but it's difficult to infer where it starts and where it ends. So that's an inferred boundary. But from Tranquility Bay west all the way to Great Bay, you can actually see there's a definite two-tiered system of reef growth in those two areas. Now let's move on to the north coast. So in Western Rio Bueno, what we have is this heavily calcified, taphonomically degraded Acropora palmata class and stance. So we have, it's both in situ and it's ex situ. So it's a mix of them. And then just behind that, so about 100 meters behind that, we have a carbonate mud, and it shows this vertical succession into a coral framework. It's abundant with Siderastria siderea. The corals are floating in the carbonate mud, so they're not ex situ, they didn't fall into it. So they're actually growing and then they're getting smothered by the mud. And you can see that if you look at it, you can find a lot of these instances of partial mortality, and you can find these very elongated growth forms in the Siderastria. In Eastern Rio Bueno, you can see in A, we have this thick layer of parietes species, so branching parietes, and it's underlain by these basal massive corals. And at the top of it, we have this calcified cap, which I think is probably just due to case hardening. About 50 meters away, we have scenic view, which where we see these patch reef structures. Now, these patch reef structures are consisting mostly of Orbicella annularis. At the top of them, they're encrusted by Undaria agaricites, which is a lettuce coral, and Parietes asteroides. So, and then they grade very rapidly after that into these into Parietes fraccata. So the same thick layer that we see in E. And next to that, at C, we can actually see the foundation where the reef started growing. So that's the Hope Gate formation. And the foundation that the Falmouth grows in just happens to be whichever substrate is available at the time. So in Port Maria, it might be the Manchineal formation. In Treasure Beach, it could be the Newport formation or the Augustine formation. So it's just whatever it happens to be available to colonize. And this is the biofacies map of Rio Bueno. I've adjusted the sea level to also be 6 meters higher here. So what you can see, we have facies E, which is abundant Siderastria growing with carbonate mud. We have facies F, which is a mixed in situ rubble with the Acropora palmata framework. It's heavily calcified and taphonomically degraded. We have we have facies G, which is the basal massive coral heads overgrown by Parietes, which we see in the eastern part of Rio Bueno. And then we have facies H, which is the large Orbicella annularis patch reefs. Those colonies are overgrown by Undaria agaricites. And then there's the overgrowth of the branching Parietes corals. And this is the representation of that. So we have much more continuous units in this case. So we have this continuous Parietes, branching Parietes. There's a layer of Siderastria species in the eastern Rio Bueno section. It's not continuous, but it's there. And then in the western Rio Bueno section, then we have the same Siderastria growing in the mud, the carbonate mud, and then that very rapidly it laterally transforms to this reef crest species. So the way that, so based on the samples, a total of 37 samples were analyzed. 22 of them were from Treasure Beach, 15 of them were from Rio Bueno. The breakdown of them is there. So connected from Tranquility Bay, Great Bay, Frenchman's Bay, Billy's Bay, and Western and Eastern Rio Bueno. 21 of them are Aquapora palmata, 9 are Pseudoastrea, 5 are Porites, and 2 are Oricella annularis. And 4 slabs were made from each specimen, and there was an attempt to keep the thickness of the slabs even. This is how the slabs are characterized. So the first thing I would do is find the secondary porosity of the entire slab. Then I would find the secondary porosity of the coral. After I found that, then I would see how much of it is due to bioerosion, how much is due to dissolution. For the amount that's due to bioerosion, I try to classify them as best I can into the respective ichnogenera. So you can see those here. So you have these are macroborers, and I identified them using classical text. So Bromley and D'Alessandro, Ed and Jean Riss for the sponges, and Kelly and Bromley for the bivalves. So, and you can see here some examples of it. So in the upper left-hand side, you can see Tripanites, which is this J-shaped chamber. There's Entopia rectiformis, which is this linear multi-chambered multi-camerate chambers. And then there's Entopia glomerata, which is one chamber. It's one large chamber with a single aperture. There's Gastrocanalites torpedo, which you can see in the lower left-hand side. That's made by bivalves. And in this case, it's infilled by sediment. So that's sediment occlusion. And then in the upper right-hand side, you can see Rogarella, which is a barnacle. It's a passive borer, so the coral actually goes around the barnacle. Tripanites is a polychaete worm, so these are worms in the coral. Entopia is sponge, right? And using this, I was able to quantify exactly what area was bored by which type of macroborer. Now this is a ball and a 3D ball and line plot, and it's just to help me to visualize which species, if there are any distinct groups. And there is one distinct group that you can see in the dendrogram on the right-hand side. So you can see all of these Great Bay corals along with the Aquapora palmata from the Western Rio Bueno corals in pink. So they form one distinct group in this dendrogram. Might be easier to look at it here, and we can see exactly which processes are dominant in which areas. So in Billy's Bay, sediment occlusion is the dominant process. In Frenchman's Bay, it's bioerosion. Great Bay and Western Rio Bueno, both of those are dominated by incrustation. Tranquility Bay dominated by sediment occlusion. And Eastern Rio Bueno, pretty low values for all of them, but still dominated by bioerosion. Now the actual macroborer analysis in the South Coast reefs, with the exception of Great Bay, all of them are dominated by sponges, which is consistent with modern coral reefs. In Rio Bueno, it's different. In Western Rio Bueno, it's dominated by bivalves, and in Eastern Rio Bueno, it's dominated by worms. The barnacles are found exclusively in Porites asteroides, so they're species specific, but I still counted them. And that can give us an idea of some of the paleo-environmental conditions that these corals were experiencing. So based on those, based on the taxonomy, the quantitative taxonomy, I put together this semi-quantitative, well, qualitative taxonomic species. And this is based on the same things that we looked at: the bioerosion, the sediment occlusion, and the incrustation. So in the case of, So in the case of Belize Bay, Taphofacies D, which is associated with fish, biofacies D that we looked at, we have extensive entobia bioerosion, which associates with high turbidity stress on the coral and high rates of partial mortality. Discontinuous patchy growth of encrusters, and that's associated with a high rate of coral growth and coral overgrowth and difficulty of the encrusters to establish due to rapid burial. And there's a lack of sediment occlusion within the borings themselves, but there is a rapid accumulation outside the coral. And this could be due to rapid burial of the coral class. And this gets interpreted as the rare zone of the reef crest into the shallow back reef. Taphofacies C, which is from Frenchman's Bay, we have the erosion and dissolution of the surface of the hemispherical coral heads. That could be because it's reached maximum, it's grown to the accommodation space, and siderastria radians could be an indication of a transition to a more lagoonal environment. So I categorize this as a recolonized reef reservoir. Taphofacies B1, which is Tranquility Bay, and this is associated with biofacies B1. These have extensive lines of regrowth in the internal coral framework. So that means that we have high rates of partial mortality in the coral. There's sediment occlusion within the borings, and that means that we have high rates of sedimentation. There's a relatively high abundance of gastroquinolites. Gastroquinolites is associated with more turbid water conditions. So we can infer that these conditions were more sediment stressed, so turbid eutrophic conditions. And there's discontinuous encrusting sequences between the corals. So within the actual primary growth fabric of the coral, we see these discontinuous algal sequences, and that could be due to the high rate of sedimentation that won't allow for encrusters to establish themselves. Final one for Treasure Beach is Taphofacies A, and this is from Great Bay. So we have this continuous growth of encrusting communities, which means that it would have had a relatively long residence time in the taphonomically active zone. The internal geopetal structures face up, right? So geopetal structures are borings that may have been partially infilled with sediment, and they give a good idea of which direction the organism is facing when it was growing. So in this case, they face up. So that means there's no overturning. And there's some minor syn deposition of sediment between the coral fronts. So that means that there may have been minor sedimentation, and the incrustation outpaced the sediment accumulation, unlike what we saw in Tranquility Bay. Taphofacies F is Western Rio Bueno. So there's variability in the incrustation between the Acropora palmata class. And that means that there's variability in the time spent between, in the taphonomically active zone for different class. The internal geopetal structures, at least the ones that I've collected, are overturned. So when we collect the corals, we mark which direction we've extracted them in. And then when we cut them open, if we see a geopetal structure, we can see if the geopetal structure matches the direction that we marked when we took out the coral. If it doesn't, it means it's been overturned when it was deposited. And so that means that it's not in the light position, and that could have some implications for the current energy that could have resulted from breakage of the coral. The surfaces of some of the class are taphonomically degraded. And that can mean that there's high current energy, and then the class are remaining in the erosion cycle that's breaking them down and smoothing them. So the depositional environment that I interpret here is the reef flat with some type of storm influence. There is something that looks like a truncation surface within Western Rio Bueno. So that's where the storm influence came from, in addition to the overturning of the reef crest of the Acropora palmata class. And then finally, Taphofacies H. So this is from Eastern Rio Bueno, and it's associated with biofacies H. And what we see here is we have sediment infill within the primary growth framework. So the actual way that the coral is growing is overgrowing on itself. And those spaces that it's leaving are being infilled by sediment. There's a thin algal crust in the internal growth fabric. So that could imply rapid sediment burial. And the surfaces of partial mortality, there are a lot of surfaces of partial mortality and regrowth, which could imply that there's significant sediment smothering taking place. So I interpret this as a patch reef in a high sedimentation environment, and these are the initial colonizing corals. So this would be part of the startup of the reef. Now, the reefs in Treasure Beach don't follow the typical coral zonation, the coral succession model that Geister put forward. So we can interpret that they're not shallowing upwards. So usually a reef would, if we were to just have a bare substrate and a reef was to start to grow on it, we would see a shallowing upward sequence. We don't see that in Treasure Beach. What we see is something more like a restricting upward sequence. So we have these lagoonal and back reef deposits at Tranquility Bay, and this makes a case for progradation. So if we have these back reef deposits overlying more open water aquapora deposits, it means that something is causing that to be more restricted. And that can make the case that perhaps there's a reef crest that's going further offshore that's restricting the area behind it. And that may result in an initial give-up phase for the Acropora palmata, followed by the establishment of the lagoonal species associated with the higher water, quieter, higher turbidity coral environments. So this is the depositional model that I came up with for Treasure Beach. One of the things that you can see is there's a sea level jump. So I associate the lower Acropora palmata units with the first sea level, SL1. And that first sea level, that's evidenced by, that's associated also with the massive coral heads that we see in Frenchman's Bay. And when we have a sea level jump, I think that there's progradation that's taking place. So we have the lower reef unit that's unencrusted, and then we have the sea level jump where we have progradation of the upper reef unit that we see in Great Bay. And that triggers the transition from these more open water environments to a more shallow water, a more restricted environment. Also, the reef crest might be the paleo reef crest might be the source of the Acropora palmata rubble that we see in Billy's Bay. The reef flat that is going on, so the new reef crest, I think, has a remnant in Great Bay, where we saw those monospecific Acropora palmata stands growing on this truncated surface of Acropora rubble and planed off massive coral heads. So I think that's an indication that the reef would have reached the accommodation space, and then there would have been a jump in sea level that would have triggered much more, a significant increase in accommodation space over a relatively short period of time. And that would have triggered the growth of the reef crest, the progradation of the reef crest to the south, and the transition to the back reef and lagoonal fishes at Tranquility Bay. Now, in this particular case, I think it's limited by accommodation space. The fact that we can see any of the reef geometry at all, any changes in the reef geometry or the reef fishes, is because of a limited accommodation space. And that's one of the things that I put forward, is that accommodation space is the main factor in determining whether or not we can see any of these sea level changes. This is the depositional model for Eastern Rio Bueno. So what I put forward here is that we have these initial patch reef colonizing species, the Orbicella annularis. And within the Orbicella annularis, as we saw earlier, we have overroofing. So we have the coral framework, it's growing over itself. And that's indicative of what we call a superstratal reef growth. So the corals are outpacing the sediment accumulation around them. So I would interpret this as a catch-up phase, the initial catch-up phase of reef growth. And that would have, and this high sedimentation could have been caused by the initial flooding of the platform. The death of the patch reef itself could have been caused by some change in environmental factors, and we can see that as evidenced by the Agroscites and the Porites asteroides colonizing the tops of the patch reef sequences. These are coral species usually associated with some kind of environmental disturbance. Now, the thing here is that sea level may explain why we see a species change in this area, or it may explain the death of the patch reefs, but it isn't a definitive explanation. And that relates back to what I said earlier. These patch reefs were still in the catch-up phase when they died. So they were still trying to fill the accommodation space. So when they died, it wouldn't have, if there was a change in sea level, it wouldn't have, you wouldn't see it reflected in the facies, in the vertical facies changes. But a change in sea level would explain why the lagoon would explain a higher sedimentation rate or a higher rate of turbidity, which would have put further stress on the patch reef sequences and would have resulted in the rapid aggradation of the surrounding lagoonal facies with the Porites, with the branching Porites species. So the conclusions that I reached, so there are 5 biofascies and 4 associated taphophases that we can observe in Treasure Beach, 4 biofascies and 2 associated taphophases that we observe in Rio Bueno. Treasure Beach shows evidence of a sea level jump and the progression of a new reef crest. Rio Bueno shows evidence of environmental disturbance that may have been driven by sea level rise, resulting in the death and the burial of the patch reefs. The main determinant factor in the geometry of the reef facies is the antecedent accommodation space when the sea level jump actually happened. So if we have the accommodation space being filled up at the time of the sea level jump, then it's more likely to be reflected than if we have a reef that's in the initial stages of growth and then there's a sea level jump. We wouldn't be able to necessarily see exactly, we wouldn't be able to see that distinct change in species that we can see in Treasure Beach. So which sea level model best can be best applied to what we see in Treasure Beach? Well, that's the Yucatan model by Blanchard, where we see one phase of initial reef growth and then another jump. I don't see any evidence of intervening low stand in Treasure Beach. There are some areas where they may have some erosion, but I don't see any evidence of subaerial exposure that you would expect to see. Things like rhizocretions or paleosalts or anything like that. It could be that the sea level, that any intervening low stand wouldn't be long enough for those things to appear, but so far the Blanchard model seems like the most useful model in explaining the species distribution. So to conclude, changes in sea level are more likely to be preserved in the reef record along reef tracts limited by accommodation space. So that's the general thing that I'd like to get across by comparing these 2 environments. So future work that I'd like to do, I'm still working on dating some of the corals that we've recovered from these sites. It would be useful if we can figure out the accretion rates and compare the accretion rates of the late Pleistocene to modern coral reefs. And also I'm looking at going further west of Belize Bay in St. Elizabeth, but we've explored it a bit, but I haven't mapped it out as in any detailed way. You can actually see where the corals establish themselves in the center photo, Dr. Stemman. So you can see where they actually establish themselves on that limestone platform. think it might be the Augustan Formation, but we're not sure as yet. And just the final thought, a lot of this is based on sea level, on the sea level model being 6 meters higher, being sea level in the last interglacial warm period being 6 meters higher. So I went to the GSA this year, and one of the papers that I keep hearing a lot about is this one. And it puts forward that actually most of the sea level value that we see in the Bahamas is actually a relic of glacial isostatic adjustment. And that there's a 95% chance that sea level in the last interglacial didn't reach past 1.5 meters. If that is true, it would have implications for the uplift rates, because uplift rates would be overestimated, subsidence rates would be, uplift rates would be underestimated and subsidence rates would be overestimated. So it would be interesting to see where that goes. Thank you to Dr. Stemon, who's been incredibly helpful and accessible through all of this. Dr. Blissett and Professor Mitchell, who've always been willing to give me advice, and Rashawn and Brian, who've been helping with processing these samples, and my fellow postgrads and the Office of Graduate Studies for funding, partially funding the research. Okay, so I hope we still have time for questions. Thank you.
We have lots of time for questions, Matthew. You had good timing today. First of all, let me offer my congratulations to you on what is a tremendous piece of work, very comprehensive, extremely well presented. You made it very accessible, I think, even to persons who are not geologists. And I was going to start by leading off on the commendations for the work you've done and what you presented today. And you have your first hand from Professor Mitchell.
Okay. It's a few little comments and then a few questions. Okay. I wouldn't extend Augustown as far as Treasure Beach. I think it dies out beforehand. I don't know what I would call it, but I don't think it's Augustown by the time we got there. It's lower coastal group of some description. There's no doubts about it. I mean, you know it and you've seen it, and it's sort of full of spherogypsina and things like this. So, but I'm very interested in that. But you started off in your presentation of talking about tectonics as well, and you didn't sort of raise the idea that maybe tectonics are important down in the Treasure Beach area. And of course, you do have that funny bit of white limestone lifted up just south of your current study area, whatever they call it, Pedro, whatever they call it. What do they call it?
Pedro Bluff.
Yeah, Pedro Bluff. And that's weird. It seems to be fault bounded, maybe on all sides, and it doesn't have reefs on top, which may be indicating there is some tectonics going on in there. So could tectonics be playing a game as well?
I think tectonics could be, well, definitely there is some tectonic, there's tectonics involved. To the extent that it's been explored, it's had to do mostly with post-depositional movements or post-depositional subsidence or uplift. As for syn-depositional, I think it could be playing a role in the maybe the antecedent topography that the reef is going on. I think that might probably be where it would be playing a role. That particular in the south, in southern Jamaica, I think is the topography is a lot more shallow, so it would make sense that perhaps since there might be less accommodation space to fill, then you end up with the cores filling the accommodation space much more rapidly.
Dr. Miller's not here. I don't think he's on here anyway. but he will have identified a dome situation situated sort of more along the coast to the northwest of your area, which I can map out geologically as showing the white limestone in the core and the lower coastal group sitting down on both sides. And that again suggests some quite young tectonics going in the area, both of those observations. So I just think, I'm not saying it is tectonics. I just say, I don't think you should exclude it. That's the point. And I wonder if, you're saying you're going to go up further to the west. Have you been to the east of Pedro Bluff?
No, I have not.
There's it's a really nasty area to get into because you have to walk through basically what looks like a desert with windblown sand and things. But there's an awful lot of Pleistocene reefs out in that direction as well. And that may well be worth a look at as something just to, add to it. If you're going to go back to that area, at least spend a day out there early on and just see if it makes sense that you actually spend any more time there and look at it. And there's some really quite interesting taphonomic features that we never ever got round to describing from there. And there are places where you have the regular echinoids with their spines attached to them, and they're just buried in the sediment, which is another interesting taphonomic process that perhaps you could throw some light on.
Okay.
I'm just saying that there's a lot more in that area than maybe. Did recently, a couple of years ago, there was somebody who did a project on that area from a university, and I can't remember where it was at the moment. I should remember, but I can't remember. Did they do any dating on these rocks?
They did dating on some of, but their stuff was actually west of where I was studying. So I don't think they did the Treasure Beach area. They did electron spin resonance dating on some of those. So
does it make any sense to you, or does it not make any sense, or can you not really work it out at the moment?
I can't work it out at the moment, but some of the dates I remember looking at, the uncertainty range was pretty high. So
I know, I understand that, and yeah, so they didn't get everything right in there, but I mean, it's something that exists. Maybe it's not correct, but I think, yeah, you have to recognize those sorts of things. And it takes me back down to the places we used to look around Port Morant, obviously many years ago now, where I definitely have two cycles in the clastic stuff there. And it's sort of rather nice to see two cycles, and you'll sort of say two cycles down in some of these other places as well. And that sort of is rather nice. And you do sort of wonder, but of course, as you jolly well know, most of the corals are pretty much blasted, and finding something nice or aragonitic is not as easy as you might wish to find. But I am very interested. I wish you luck in going forward with this, and I think it's very interesting and will be something that, well, I hope you'll get at least several publications out of when you complete it, as well as your degree. So thank you for a very nice presentation.
Thank you for your comments, sir. I really appreciate them.
Thank you, Simon. Really interesting engagement. I just have one quick question. You mentioned for your future work to look at microtaphonomic signatures. Why do you think it would be worthwhile pursuing that particular line of investigation?
Well, the first thing I would like to look at is to start identifying the actual species that are encrusting some of these corals. So by identifying some of the actual species, it helps to refine even more what are the events taking place after the coral dies, as opposed to just these general things of burial and these general processes. So I would like to look at specifically looking at that, and it helps with delineating things like storms or things where you have, or events where you have sea level rise or sea level fall. So that is that would be the main reason. They're very useful in helping to delineate sea level responses. So that's why I would like to look more closely at the microtaphonomic features. And also in addition to that, they're useful in helping to look at the timing of some of the taphonomic processes. So do you have fractures taking place before you have bioerosion? Do you have some kind of stress, some kind of burial that might be indicated in fractures? So that's why I would like to look at it. Yeah.
All very good reasons. I just wanted to kind of probe a little further. And I see that Professor Mitchell's hand is back up for part 2 of his either a comment or a question. So I'm acknowledging Simon.
I think it's simply just back to what was being said, and that is that you're talking about the microtaphonomic changes. Do you think you can put these microtaphonomic changes into changes of environment over time, which might work very nicely? In other words, you can then start working out what's going on. In other words, do you get some calcrete sometime at some point developing in there? Or do you think it's just the evolution of the individual reef and its growth and its decay and its breakdown and that sort of thing? So in other words, do you think it's a local thing, just within the normal sea level? Do you think it's more driven out by the changing sea level sort of processes you've sort of implied?
So I think that the main, how do I put this? I think that the main features that you can find, the main vertical changes in species that you can find. So let's take the treasure beach area since it's the more interesting one. The main vertical changes in species that you can find in that area are more driven by, well, for one, sea level change, at least at that scale, and then probably flooding of the local area, flooding of maybe the coastal plains that might lead to some kind of remobilization of sediment, and that might also affect the back reef fishes. But as for like the larger tectonic story, I think
even sea level story. I mean, yeah. This could be a sea level. I mean, it could be 2 sea level rises, and maybe between them you maybe can sort it out taphonomically. I don't know.
There's also a question from Dr. Stemon. So just
yes.
Okay.
I'm not going to go on.
No, they're continuing.
I'll talk to him afterwards.
Yeah. No, just continuing. Yeah, I actually, and one of the problems is dating a lot of the material in many places to get detailed dates. So the Southwest area is going to be some of the best places in Jamaica to get nice, pristine aragonite.
It's pretty
yeah.
to start with, yes.
Yeah, and we have not yet made it eastward. I keep thinking about that. It's been maybe 1999 since we were there.
Yeah. Take lots and lots of water. That's what I would say with you. It's extremely dry as you go that way, and it's a long walk across those dunes around the back of the Pedro Bluff, and it's a long walk in, and it is extremely dry there. So you need loads and loads of water. But I think it would be interesting.
That would be,
Matthew, I think you'd enjoy it. That's the point. I think you would really find it quite interesting. And it might complement what you're seeing out there. That's the point.
And of course, very different environment in terms of you've got essentially something fringing directly on what would
I agree. It's very different. It's very different. And I think it would be really good. And I think it would be really worthwhile that Matthew goes out and looks at it. I think it would be brilliant.
And the stuff we've investigated further west is also really interesting. There's some neat major changes that, well, I don't want to ruin it for him later. He'll be able to discuss some of that. One of the things I do have a question on the geopedal structures up in the Rio Bueno acropora. And this, to me, it's interesting because you're actually talking about some very early lithification of the sediment. If the corals are getting, I guess, bio-eroded, then some sediment inclusion, that must cement early, and then they're being transported, broken and transported. So it's essentially because the sediment, unless we're imagining them breaking and then getting moved again, but we're still talking about some pretty early cementation of the sediment, it seems to me.
Yeah, I think that's what it is. And even there you can see that it's very castified. So but I think what it is that you have these corals that are growing, and then they get they get eroded. Well, sorry, they get bored. You have some partial sediment infill, and then they get broken up. And you can see some overroofing structures within those corals themselves, within the aquapora that you find there. So it says that after they're broken, some of them are still growing.
Yeah,
and
well,
then
they would be, yeah.
So that could probably, I mean, it could explain, maybe they're not dead when they get broken up, and they're still growing. And then
yeah, that is true. And that's the way a lot of those corals spread. They actually literally, the breakup is one way for them to reproduce. They essentially break up and then regrow. One of the things I was thinking of was the characteristics of the sediment in the East Rio Bueno. Is it different in the Porites and around the patch reefs? Are we looking at more restricted, because the thin branches that cap those, you expect to be in more restricted, less wave washed environments. I don't know if you've looked in detail at that, because that also might help tell the story of what's going on in this that pattern.
The thing with Eastern Rio Bueno, I think, is that it's so because I think that it's when the patch reefs died, they were still relatively young, right? So they were still in that catch-up phase. So it's difficult to say if you have since all of it is back reef deposits, so back reef to lagoon deposits, it's difficult to say if you have a reef crest that's causing that really thick progradation. I think what it could be is maybe an increasing sediment stress that might be keeping pace with the growth of the Porites corals.
Yeah, that's still hard. It's hard to say, but that's often they do grow that way. Those thin branches essentially grow up through sediment. And that a lot of sediment would certainly spell the end of the massive corals. They wouldn't be able to, perhaps. I'm not sure if that's the thing.
The one thing that I did.
Well, I'm going to. We're losing a few people.
Okay.
One thing that I would like to say is that it's very obvious that certainly among the geologists that Matthew, you've managed to stimulate some very, very exciting debates about what you have found so far. And I would just like to encourage Dr. Stemmen and Professor Mitchell to continue the engagement, maybe up there somewhere, either Rio Bueno or Treasure Beach, looking at stuff.
Yeah,
I think what I think it needs is some sort of discussion about it and then pointers. I don't know the answers myself.
But that's why
that's the point about this. I don't know the answers.
That's why you're going to continue the discussion.
This is why it's interesting, because I want to see what the answers might be, or what an interpretation of the answers might be, and that's the whole point about these things. And I think it's interesting, and I think these are very interesting areas. I always take it back to basically St. Thomas and try and play it with what's there. But of course, the different parts of Jamaica, they might have gone through very different tectonic phases.
Yeah.
And we don't know if it's, we don't really know whether we've got sea level changes or whether we've got a single, if we got a tectonic event that does things. I mean, as Matthew has said, this stuff rests on whatever it wants to rest on, wherever it is.
All right.
We
Thank
have a
you.
big tectonic
Thank
thing.
you.
So.
So we're gonna go. Matthew, thank you. Presidential Student Emma, engaging Matthew on the presentation. But more so, I would like to thank the persons who attended. Every week we have some guests that drop in. I see that Junior Prosper again joined us from Antigua. Dr. David Smith from ISD has dropped in. And so we encourage you to share the word that the link you got today connects to a brown bag every week on a Thursday at 1 o'clock. So do come at some other time to see what else the staff, postgraduates, or guests of the department are doing in their own research at their institution. So thank you all for attending this week's presentation. And I look forward to moderating next week's session with all of you back again, if not most of you. Thank you so much.
Dr. Edwards.